So today I want to talk about some of the recent work we have been doing in exploring Polaronic effects in various different systems, ranging from more type condensed matter systems to cold atomic systems. And this was done work in theoretical collaboration with Eugene Demler and Hossein Sadishpour in Harvard, Atachi Mamoglu at ETH Zurich, Michael Fleischhauer in Kaiserslautern, and you heard already yesterday about the work we have been doing together with Michel Emeshko here in Vienna. And there are also a lot of theory collaborations we have been working in. So as physicists, we try to address phenomena which take place on vastly different scales, ranging from nanokelvin in the cold atomic lab to, let's say, giga-electron volts or mega-electron volts if you think about the nuclear physics. And somewhere in between is room temperature. And in some sense, it might be a little bit intimidating that we have to describe all these different scales and phenomena on these scales, and with the limited tools we have. But there's a concept of universality which comes to our help, namely that the same low energy Hamiltonians are often sufficient to describe these phenomena on these different scales. Because as we heard on a slide, I forgot which one it was, we have to divide, for instance, to get universal quantities, but let's say TC, for instance, and get a universal curve. So actually, we are often in the situation that we can describe these phenomena with the same low energy models. So let me give you a couple of examples. The phenomenon of Bose-Einstein condensation was first observed in cold atoms in 1995, and it took then about only 10 years later that for the first time exciton polariton condensation was reached in semiconductor structures. Actually, temperature scales about 10 orders of magnitude higher. A second example comes actually from nuclear physics. In the 70s, Vitaly Efimov was studying C12 nuclear resonances, and was thinking about maybe these are actually 3 alpha particles which could bind together. And in the course of solving the low energy Schrödinger equation, he actually found there should be exotic 3-body bound states. And these were, however, never directly found in the context of nuclear physics. But about 40 years later, on completely the other side of these scales, again in cold atoms, his prediction was then observed. Actually, now, I think 3 years ago, the helium trimers were actually observed in the group in Frankfurt, which were somewhere here in the middle. And these are just 2 examples to show, for instance, that we can use semiconductors and cold atoms to actually explore jointly a universal phenomena of quantum many-body physics. And this will be a little bit the line of my talk here to show some of these universal connections. One universal challenge we as theorists face are happening in systems where we have a strong interplay between few and many-body physics. So if we just consider a few-body problem, let's say we solve bound state problems, it might be molecules or excitons and trions and semiconductors, we can actually often rely on the powerful theoretical tools, namely solving, for instance, the Schrödinger equation using wave mechanics. On the other hand, also often, when considering many-body physics, we are sometimes safe, namely when we can map the problem in a mean field setting on an effectively non-interacting one. A famous example is the theory of BCS superconductivity. It becomes a little bit more tricky if there's a strong interplay between few and many-body physics, namely when we do not know, for instance, which composite operator takes an expectation value in many-body physics. And we have to solve the short-distance problem, but also consider the long-distance problem. And this also happens naturally in the non-equilibrium setting. Very short timescales, the particles will scatter with each other, that's dominated by few-body physics. And only at longer timescales, collective phenomena set in, and we have to address the many-body physics. Now, a natural system where we can study such a strong interplay in a very detailed way, in some sense, are actually quantum impurity problems. We have a single impurity in the bath. And when I say impurity, I do not mean defect. What I mean is something else and something different. So this can be a mobile particle. This might be an electron in the bath of phonons. And we can ask them questions, can we actually use such impurities as a sensing tool also of the environment? We can study polaron formation, or we can even ask, can we actually control an environment by a single particle? And Polaronic effects, the tracing of an impurity, I mean, this is the conference for that, by a bath, such Polaronic effects appear in a lot of different settings. We have been working on, for instance, such phenomena in cold atoms, in the context, let's say, of magnetic or Bose polarons, or in the context of the fast tracing, the real-time formation of Fermi polarons in cold atomic gases. Then one can also use them as sensing devices, quantum impurities in a sense, also NV centers. You can call a quantum impurity problem where we study, for instance, the sensing of the charge transport in graphene. And excitons, for instance, quantum impurities appear also in a sense as excitons which can interact with a bath of electrons in semiconductors, which will be the last part of my talk. Also, they appear in more hybrid systems. Michal Imeshko was talking about this. We can also understand, or try to understand, the modified rotational spectroscopy of molecules in superfluid helium nanodroplets in the terms of not a translational moving a particle, but a rotating particle which becomes stressed and gets a renormalized, not effective mass, but rotational constant. And what I will also talk about a little bit, they appear also in the quantum optics setting in the sense that Rydberg excitations in cold atomic gases and Rydberg EIT experiments can be understood from a polaron perspective. So the three topics I will shortly cover, it's just more like a short overview, and please bug me later for the next couple of hours or over email or the next conference. So the first part of the talk will be what I call strong coupling Bose polarons in cold atomic systems. These are impurities which interact with the bath via short-range interactions, which are tunable via Feshbach resonances. And here we will deal with tracing mostly with low-energy bath excitations. In the second part, we will still consider a single impurity in the Bose gas, but this time there will be long-range interactions, and the tracing doesn't happen with low-energy excitations, but actually with high-energy bound states. And this gives rise to a new kind of tracing mechanism, a little bit related to spin polarons. And in the last part, I will shortly discuss excitons and doped atomically thin semiconductors. So I don't have to show you this slide. If you want, and I still do it, if you want to understand polaron formation, let's take this Fröhlich Hamiltonian at length discussed this morning by Robert Zeiringer, for instance, also now here without the Lilo-Pines transformation. If you want to understand the formation of a polaron, we have an impurity interacting with a bath of phonons. It changes its motional state P by the emission of a phonon into a state P minus Q. I can write this down in such a variation of wave function. Actually, for fermions, this was for the first time written down in the context of cold atoms by Frédéric Chevy here. And Suris did this 10 years before in semiconductor systems. If we transform this wave function to real space, conditional density with respect to the distance from the impurity, this term would just be a flat distribution of the background BEC. If you take the Fourier transform, including this variational term, what we find is the polarization cloud. It's kind of like if you would talk to the phonons, that would be the stuff which you would actually test in this experiment. So this is not the waffle state, though. This composite object, of course, impurity plus polarization cloud is the Bose polaron, and we have our quasi-particle properties. All right, so the question is, let's actually crank up the tracing of our impurity by the bath. How do we do this? We increase V. Best would be to increase it to infinity, also as discussed this morning. And one way of doing this in the context of cold atoms is the following. There we could have one species of atoms, let's say a lithium atom, immersed in the potassium-40 BEC or so. No, potassium-40 is a fermion, potassium-39. And then we can crank up interactions between the two species by the fact that we can, in the collision of these two atoms, they can jump into a virtual bound state and jump back. And if this virtual bound state exactly has the same energy as the scattering threshold, you get a scattering resonance. This is called a Feshbach resonance. And there the scattering length goes to infinity. The hope would be, since V in mean field theory is connected or directly proportional to the scattering length, maybe we can crank it up this way and get strong polaron tracing. Now, the problem is, though, if you want to crank up actually this interaction strength, we have seen we need a bound state. But to actually get a bound state, it's not sufficient to have an impurity traveling in the system, catching an atom from the BEC, this is a phonon excitation, and then emitting this phonon back into the BEC, because for binding, you actually have to have the repeated scattering of phonons. And this actually you can show in the renormalization group study that this corresponds to a dangerously RG-relevant term in this Hamiltonian, which you have to take into account. And this is what we showed in 2013 in the paper, that for the description of strong coupling boson polarons and cold atoms, this is an additional term you have to take into account. The Fröhlich Hamiltonian will not work at strong coupling. And there have been a bunch of actually extensions and studies of this Hamiltonian since then. I stopped in 2016 or so putting the reference in, so that there actually had been many more papers since then. How do we observe our boson polarons and cold atoms? Transport experiments are hard. Since it's not so easy for experimenters to put a force on the single impurity, what is much easier is to do basically not optical but RF experiments, where you prepare an impurity or put an impurity in the bosines and condensate, for instance, and the impurity can have two different internal states. If it's in an electronic, let's call it 1 state, it doesn't see the environment. If it's in the electronic 2 state, in some excited state, can be a hyperfine state, it can see the environment and interact with the environment. So that's basically as if you would create in a semiconductor an exciton at some point. The exciton, of course, interacts with the phonons and the environment becomes a polaron shift, but before the exciton is there is not even such a concept. So it's very much like an experiment in a semiconductor. Then Fermi's golden rule for the absorption tells you have to start from the initial state of the system, impurity momentum P, BEC, and then you have to sum over all possible final states, including the interactions, and one of the possible eigenstates is the ground state polaron. And there you should see a nice peak in the spectrum with a height given by the quasi-particle weight. Now one can calculate this absorption spectrum, and I show it here, frequency, the absorption spectrum, as function of the attractive interaction strength. Very weak attraction, very strong attraction. And the tuning parameter is here the scattering length or the inverse scattering length. So if you have very weak attraction, well, we get a typical attractive polaron shift. We basically have a phonon cloud surrounding the impurity if you go to real space. If we crank up interaction further and further, actually what will happen is that there's a crossover to molecular state. Basically the impurity catches one of the phonons or the bound state. It's actually not a phonon then anymore because it's actually in the dispersion branch of a free particle. It builds a molecule which then is a molecular polaron in the surrounding environment. And only very high up in energy, there appears a new quasi-particle state which is metastable, so it has a short lifetime, which is a repulsive polaron, which actually pushes away the surrounding environment. So that's so this setting here comes or is due to the fact that we have this additional RG relevant term in the Hamiltonian. Now one can go to the experiment, luckily, and do exactly this RF experiment, and this is what the group of Debbie Jin and Eric Cornell did at Gila, and I also show a slide of actually Jan Alt, who did the experiment. Basically, yeah, they appeared, as you can see here, on the same day in PRL. I show here Debbie Jin's experiment, where we can see here the experimental results for the measurement of this peak as dots and our theoretical predictions in this extended Fröhlich model, and there is fairly good agreement. The Fröhlich model would actually predict this energy here, but it's just not the correct model for such experiments. Since they are also theorists, of course, let's just briefly mention what we actually did for this calculation. So one can do something which is called a non-self-consistent 2pi resummation. You calculate the T matrix, basically the in-medium scattering of the impurity with the bosons, and then you insert this back into the self-energy of the polaron. This gives you this spectrum here. Observe there is a gap actually between the polaron ground state and the excited states. And this gap is actually an artifact of the theory. In fact, such a diagrammatic expansion is the same as using such a variational ansatz. Now, this includes, as you can see, just a single boson excitation, which you use to dress up the particle. And of course, as we learned this morning also, there's a PK-Ansatz, which is a coherent state ansatz, which would include infinitely many excitations, so one can also test that. What we did first on the field theory side is actually we did the self-consistent scheme, where we back insert the self-energy into these diagrams, which includes an infinitely many particle Hall excitations and gives you a broad spectrum then in the response. And if you do this time-dependent PK-Ansatz, which was mentioned on the conclusion slide also of Robert Zeiringer, you can calculate using a time-dependent variational principle. So it's kind of a time-dependent mean field theory. You can also calculate the spectrum and get a broad response close to unitarity. And you would find for non-interacting BEC, that is for phonons with a quadratic dispersion relation, the non-existence of a quasi-particle at unitarity. So the Z factor is actually 0. All right, let me briefly mention the experiment also by Jan Alt here, although he will probably talk about that. He measured also this RF spectrum, which can be compared with the theoretical prediction. And here is a line cut for the RF spectrum at a very strong attraction or strong interactions at a unitarity. And the experimental data is the broad spectrum here. And then one can compare it to different theories. A single particle Hall excitation, which is kind of one calls now conventionally the Chevy ansatz, which gives you this response here. One can then go further to two particle Hall excitations, which the theory collaboration did in this paper with Jan Alt. And one sees there would be still a prediction of sharp spectral lines. But if one does the time-dependent mean field approach, which includes infinitely many particle Hall excitations, we actually predict an intrinsic broadening of the Polaron line. And actually, if you would zoom in, you would see a little delta peak here. That's the actual Polaron ground state. The rest is a broad spectrum. And then one can also compare it to the experimental data, but I think it's still an open question. That's exactly what is going on here. A little take-home message is, though, if you want to predict the energy, you're not that bad if you use such a wave function. So a very simple theoretical approach, just non-self-consistent dichromatic resummation of such a wave function. So few particle tracing is sufficient for these type of systems. Now, in the second part, let me give you an example where this will not work anymore. And this is in the context of Polaronic effects in quantum optic systems. Namely, for instance, if you have in mind devices where we want to store light or photons for a while and actually take them out of the system at a couple of seconds later, for instance, for quantum information processing. What is done in these experiments, in so-called storage of light experiments or slow light experiments, one sends in, there's a control beam which goes through an atomic gas. Then comes a signal beam which is supposed to be stored in the system. We send in this signal beam, can store the signal beam in a spin wave of Rydberg excitations. Then we switch off the control beam and we stored our light. And then at a later time, we switch on again the control beam and read out the light. The problem is the storage time is actually limited to microseconds, and this loss of retrieved photons is often attributed to a so-called density-induced dephasing. Unfortunately, there are always bosons around here which will kick the spin wave and lead to dephasing. And the question is, well, what happens here in such systems actually on the microscopic level? Can we understand what's going on here? Why? What are the timescales here for this loss of photons? And let's zoom in. We have a spin wave composed of actual Rydberg excitations in the system. If we really zoom in closely, what we would have is an atomic cloud with blue atoms here, the ground state atoms, and one of the atoms is excited to a Rydberg state, where the Rydberg electron travels through the system on the orbit surrounding its ion. Now, this electron will scatter off neutral atoms here, and this will be an induced polarization interaction, which is attractive. So what the blue atoms effectively see is, oh yeah, there's an electron in space given by probability by its wave function squared. So what the blue atoms see is actually potential, which is a direct map of the Rydberg wave function of the electron. Now this is an attractive potential, which interestingly is so deep that it can actually catch atoms from the surrounding environment, and actually there can be the formation of molecular states. Now on the many-body scale, typical scales of cold atoms, there we have Fermi energies of the order of kilohertz, for instance, densities, which would correspond to kilohertz. These molecules are deeply bound. They are megahertz deep. Of course, for chemists, this is really not deep. But for us cold atom, many-body people, this is deep. On the other hand, they are gigantic in size. They are micrometers. So we have here an interesting interplay of short distance or high energy physics, basically deeply bound molecules which are still large, so that you have to do many-body physics. So in the few-body regime, when you have very small density in the system, you see, if you do an absorption experiment, you see nicely at zero detuning the Rydberg transition, and then there are side peaks, which are exactly these molecular states, so they are observed. And then when experimentalists in Stuttgart went to, however, a very high density regime, they saw a very broad spectral response, which was not explained. And the question is, well, you know, this is actually a quantum impurity problem. A mobile particle traveling through the system, some potential, and there are phonons in the system and excitations of bosons. So can we understand this from a Polaronic perspective? And one can again write down this extended Fröhlich Hamiltonian. We again need this new RG relevant term here because we deal with molecule formation, and we can try to address this problem now with this model. So instead of polaron formation, where we only have tracing with one excitation, for instance, to build a molecule, we need definitely 2, 3, 4, and more molecular states, which makes such wave function expansions actually very difficult on the computer in the diagonalization. So what we do instead is a functionally determined approach, which is actually taken from ideas from the description of X-ray spectroscopy of metals, where you can realize the following. What we do here basically is we have the sudden excitation of a potential in the space of different particles, where that's very much like in the metal, if I take an X-ray, create a core hole, and suddenly the electrons have to screen the core hole, and actually you can measure this as an edge response in the spectrum. And we can take the methods from X-ray spectroscopy and apply it now, not to a fermionic system, but to a bosonic system. And using this functional determinant approach, we can then predict the full spectral line shape, the absorption spectrum versus frequency of the laser. At very low density of our Bose gas, we see molecular peaks, dimers, tetramers, quintamers, I don't know how they are called when you have higher numbers. If you go to a denser gas, the spectrum changes actually to a more Gaussian distribution, which is an envelope of molecular peaks, which becomes a perfect Gaussian at very large densities of the surrounding environment. But note, this is actually not if you would zoom in, you would see that the Gaussian is an envelope of actually molecular peaks, each again being traced by a tail given by phonon excitations in the environment. And the key signature of what we call a superpolaron, because it's not really a polaron, it's a collection of spectral lines, would be a Gaussian envelope, which one should observe in experiments at high densities. And in fact, one should see then signatures of up to hundreds of atoms being bound to a single particle. So it's a gigantic molecular state in this case then. So Tom Killian at Rice University did this experiment in a strontium BEC. He first went to a very low density of his BEC, and he recorded the absorption spectrum here on the logarithmic scale. So these are actually 5 decades of signal strength. And then one can compare to our function determinant calculation, which has no fitting parameter at all, just experimental data as input. One gets actually good agreement and trust that this is a good starting point. We understand few-body physics, let's go to actually many-body physics. And then we can predict with the FDA function determinants what is the response at actually large densities. And what one finds is this very broad response. And why is it broad? I was telling you something about Gaussians. Well, the thing is, in cold atoms, unfortunately, the atomic clouds have varying density. Here it's low density regime. In the middle, this is real space, it's high densities. So you will record at the same time response from high densities and low densities. So it's actually a sum of all such spectra gives you something like that. And then you can perform the experiment, which is what, this would be the response just from the center of the cloud, a nice Gaussian on the logarithmic scale. It's x squared, basically e to the x squared, the logarithm is x squared. And you can compare to the experimental data, and it fits very nicely this Gaussian tail, which can be taken as a signature of the superpolaron formation. And actually one can, if one zooms in, even see these molecular states here would be up to 14 body-bound states. So in some sense, it's also somewhat exotic quantum chemistry, where there's extremely weakly bound molecules bound by the existence of one electron. Let me ask the chair how much time I have.
15 minutes.
Oh, I'm too fast. Let me slow down. Well, oh, I shouldn't have said that. Well, okay, we will not discuss the time now anymore. We have one answer already. So, no, I will be then quicker again. So let the chairs discuss that. But in the meantime, what one can also ask now is how would this response change if we do the whole experiments with Rydberg atoms in the fermionic gas? And one can use there then now the actual calculations which are done for X-ray spectroscopy, which is for electrons or fermions, where basically you have to consider Slater determinant states. And what you find is if you compare the response of bosons and fermions, you find that there's a suppression actually of, for instance, of the formation of trimers, here for fermions in blue, for bosons in red, pentamers, and you cannot even see pentamers. And you can also go to high densities, and there you see a compression of the spectrum for fermions. Now, this is actually rather easily understood, because what happens if you have a single excitation in a boson gas, if it's an ideal boson gas, these bosons are not correlated at all at zero temperature. Of course, if it's a thermal boson gas, we have a G2 of 2. But at zero temperature, they are not correlated. But fermions are correlated, and there's a correlation hole between two fermions. So if you bind one of them, you can be sure that the next fermion will not be so close by, so it's less probable to actually form than a trimer state. So you can actually use then this effect to actually do an in situ measurement in real time of the measurement of the G2 function of an environment in the boson gas, which we proposed and which was now measured in the group of Tom Killian again. So it's kind of a new probe using kind of this Polaronic ideas to actually measure the correlations of an environment. And let's go back to the final question here. Can we understand what's going on in the storage of light experiments? Why do these devices lose photons over time? Do we have one explanation for that in terms of basically the entanglement of these Rydberg excitations with the surrounding environment, because that's what polarons do. They entangle themselves, or impurities entangle themselves in the environment. This leads to dephasing. And one can use the functional determinants to actually predict this retrieved photon loss, and it's purely two-dimensional dephasing, or actually we can call it even the real-time formation of polarons in terms of a wave function. So basically, the wave function starts off with a non-interacting state psi, where the impurity is not interacting with the surrounding environment, psi 0. It's time evolving under a Hamiltonian H that interacts with the environment, and it loses its overlap with its initial state. Thereby, the readout laser cannot talk to it anymore. That's basically what is happening here. In the last 2 minutes, maybe 2 probably, let me say one last word about more solid state systems. Let's do half, 4 minutes then. So what we have seen is with cold atoms, they're so simple. You know, we have well understood potentials. We know how Rydberg wave functions look like, so it was super simple to do this in some sense. It's not a solid state system where we don't even probably know the band gap correctly as theorists. But since they are so clean, we can actually compare many body theories with actual experiments, and we can even hope to do stuff like that where curves actually are close by to experiments. Of course, this also works if you do really, I mean, I didn't do any hardcore DFT calculations, for instance, to calculate anything. It was just not needed here. But the question is, can we actually use the idea that actually cold atoms can be used to actually find something out about solid-state systems, and actually can we find something in solid-state systems which we later try, in the cold atom system which we later try to realize in a usable way in some sense in the solid-state systems. And this brings me to the last 2 or 3 slides about excitons and doped atomically thin semiconductors, so basically excitons and transition metal tigyl-coagenides such as molybdenum diselenide, tungsten diselenide, or the sulfides. And what I want to consider here is now not a exciton interacting with phonons, so no phonons here. it will be an impurity interacting with electrons, fermions. So since we had been talking about lattice distortions, no lattice distortions here. It will be about fermions in the environment. So how can we do this? Well, in cold atoms, it's easy. We take a lithium atom and put it in the potassium-40 gas, for instance. Instead of 39, then we have a Fermi gas. And one can do this experiment, and one will again get an absorption response which features attractive polarons, repulsive polarons, and this was the observation later in cold atoms. And there's very good agreement actually between theory and experiment here. However, here the interactions are so simple, contact interactions between the impurity and the surrounding environment, and one can actually solve this quite nicely. But what are the key ingredients to realize such a Fermi polaron, a mobile impurity in the Fermi gas? Well, the ingredients are the following. Well, it would be good if you want to do quantum calculations to be degenerate. That's easy in the solid-state systems, harder in cold atoms. But the next thing is harder in solid-state systems, maybe. We want to have a well-defined impurity quasi-particle. What it means is that the Fermi energy in the system cannot be as high as the binding energy of the object you are looking at, the impurity, or it cannot be as high as the internal transition frequencies of the object you are using as an impurity. This is well satisfied in cold atoms, where the impurity size is actually on atomic scales, angstrom, while the interparticle distances are actually on the nanometer scale. Multi-nanometer scales, optical scales, like 1,600 Bohr radii. So the question is, can we go from these kind of optical experiments in cold atoms to a little device like that? Actually, here is actually the device on which the Fermi polarons have been observed now in transition metals in the Philip Kim group at Harvard University. So it's much smaller. So to realize such a system, one could think of excitons. If you think, however, of excitons in gallium arsenide, they're only bound by 20 MeV. But if you want to insert additional fermions in the system of maybe also Fermi energy of 20 MeV, we have a problem because Fermi energies are not comparable to binding energies. So we have to get rid of this problem of weak binding. And here actually transition metal dichalcogenates, atomically thin, come into play. Basically it's graphene with a band gap due to inversion symmetry breaking along this plane here. And what we have here is, well, we get rid of the bulk semiconductor. Actually, most of the electromagnetic field lines are outside, and for instance, HBN, hexagonal boron nitride of a small dielectric constant, or even vacuum. But if you remember that hydrogen, which is basically this problem here, had a 1 over dielectric constant squared in the denominator. If you get rid of the dielectric constant, well, we get larger binding, and this happens in these systems. So what we basically have is a tightly bound exciton of a binding energy of about 300 to 500 MeV, and now we can actually gate dope our sample, introduce a Fermi level up to, let's say, 50 MeV, and we realize the Fermi polaron problem. Principle. So believing the concept of universality, this should work, and this is what the group of Atachi Mamukle tried at ETH Zurich. They have a monolayer of molybdenum diselenide. They use the fact that graphene can be used as a backgate. It's actually transparent to laser light, so you can actually use it even in an optical experiment. And you can try then to change the Fermi level, and what indeed observed in the absorption response two lines, which can then be actually compared to the theory from cold atoms, which is shown here. Actually, this paper is on the archive today, where one can compare the optical absorption here as blue shading versus the experimental result, which is kind of a hint that there are some attractive and repulsive polaron physics going on. In some sense, this is kind of now using actually this Polaronic tracing, which was found there in cold atoms, to now control the optical response of semiconductors. With this, let me come to the summary. I showed you a little bit that there's interesting new type of polaron physics happening if you go to Feshbach resonance enhanced interactions of basically Fröhlich polarons through the existence of a new coupling term. And there are a lot of open questions. In particular, is there even a quasi-particle close to the Feshbach resonance? And I think until now this is not very well resolved, neither theoretically nor experimentally. There might be even ideas to understand more real-time experiments in, for instance, context of Rydberg EIT experiments in terms of polaron formation, and as a new area where also cold atom physicists and actually solid-state physics can come together are transition metal dichalcogenides, where actually we have very similar universal physics we can explore, not only in the polaron limit, but actually also in the Bose-Fermi mixture case, where we have actually a finite density of excitons. Yeah, and with this, I would like to thank my group. So we started just last year with independent Max Planck research group at the MPQ in Garching. I want to thank my collaborators and you for your attention.
Thank you very much. So in the last part of your talk, you're talking about this Fermi polarons. Are you referring to the trine species in these two materials?
So it's a little bit tricky. So yes, partially. So if you go to here, this absorption response. So at zero Fermi energy, where we have a single electron basically, in addition to an exciton, this is exactly the trine binding energy. So if you would solve, however, this Hamiltonian, you would find two excitation branches. One is a stressed trine particle, and one is a stressed exciton, which is stressed by excitations in the fermionic environment only. The difference is the following. In absorption, and we had been having the discussions of actually van Condon overlaps. The trine has a very small oscillator strength due to its very narrow wave function. Basically, you know, we talk to excitons at zero momentum, but if they are bound to a trine, they are necessarily in the superposition state of high momentum. Thereby here the signal strength is low and you only see the exciton line here. So the trine is a different state which is orthogonal on the attractive polaron. Yeah, so the most simple way is if you do an approximation, and that's a theoretical approximation. Let's assume the exciton would be much more heavy than the fermions. Let's just assume that for a second. Here it's only a factor of 2 probably. But then there's something which is called the Fumi's theorem. Can you, for instance, read it up in let's say, Mahan or so, many-body theory. What you will find is that the polaron shift in a fermionic environment, I shouldn't call it polar in this case, it's the edge shift, would be given by the integral over the energies to the Fermi energy of the phase shift of the scattering between the electrons and the exciton. The trine line will go to first approximation if you elect recoil between the exciton and the surrounding fermions by exactly the same expression. And actually here is a minus the Fermi energy because you take one fermion out of the Fermi sea, build a trine, and then you have to sum up the phase shifts. You see, if I take the difference, it's actually nearly independent of the Fermi energy. Actually, this increase between the distance of the two lines is the Fermi energy. And you can see it to first approximation that it's almost independent by Fumi's theorem. So this is actually also in the supplementary material of the first observation of this stuff, which was not interpreted in this way by actually Mack when he was still a postdoc and wrote in 2013 his seminal paper. Yeah. So it's actually hidden far in the supplementary on some page 25 or so. No. In Eugene Demler's and Atachi Mamoukl's paper, they have overseen this reference, so it was already solved.
Okay, thank you. So for the experiments with those polarons, something that's been interesting me is that there is this fairly high density of impurities, whereas the theories look at single particles. So what's your take on that? What would be the influence of this
Yeah. So So actually just a general notion. So how these experiments are typically done, one takes impurities which don't interact with the environment, it's typically 10% of the surrounding density. Then one brings them into another state. The question is, how can it be that we don't see any effect of this high density? The answer to this is that it's theoretically, I would say, not really resolved. There are, however, a couple of things I would say. Number one, these experiments are often done on very short time scales, so we should now compare interparticle distance between impurities, take the speed of sound, and see how much time do you need to actually travel with the Fermi velocity, for instance, from one impurity to the next. Only over those time scales you can build up the correlations to build the states. However, we had this discussion before in the talk that we actually probe eigenstates of a Hamiltonian, and then you could come back with your question. Then I couldn't have a good answer to that. There are experiments by Rudi Grimm, for instance. He measures the real-time response of Fermi Polarons. He saw a small shift in the oscillation frequency in these type of pump probe experiments, which could hint to a force. And lastly, let me add to this, to look into this problem a little bit. Basically, it's kind of, you are asking about this phase diagram. Let's assume you have a large fermion density. I discussed on the point where we have a single boson. What's happening if I move out here, have a couple of more impurities in the Fermi gas? Actually, that's just mentioning briefly. This is what we did with Atachi Mamoglu with transition metal dichlorogenides, where we do a pump probe experiment, exciting a lot of excitons in the Fermi gas. And what we observe is actually, after we excite a lot of excitons, we see a blue shift, which can not only be explained by a dipolar force. If there would be not electrons around, you would see such a small blue shift. If we gate dope the sample, we get a much larger blue shift. And this hints to the fact that there's something more going on. And here, in the sense, we have a simple model of phase-space filling, but I'm not so happy about it. It couldn't explain, for instance, bipolar formation, all that. It's an open question. Basically, that's the short answer.
Another question about the Bose polaron. Do you expect corrections beyond the logarithm of approximation when the phonons interact with third order terms to be important?
Excellent point. So I completely skipped this point actually in my talk. So this stuff which I discussed would really work pretty crappily in some sense, probably in helium-4, where you have strong interactions between the bosons. So your question is basically, hey, what you did is you had boson-boson interactions. You cut everything in after second order. The problem is, then I do something and say, wow, there's a large density enhancement surrounding the impurity. Obviously, then the interactions between bosons become important, thereby corrections beyond Bogoliubov. Yes. That's, again, the short answer. Again, should be studied in more detail. Becomes only relevant, though, if you have sufficient boson-boson interactions in your system. Basically, again, divide the size of the polaron cloud by the scattering length between the bosons. This gives you probably a rough estimate how important, or you have to compare those scales.
Can you characterize these Rydberg polarons in terms of effective mass and possible productivity?
Yes and no. I can very well characterize it by quasi-particle weights. Those we can calculate. They are finite for every single peak under this Gaussian response. The effective mass is a different challenge because we did the Lilo-Pines transformation as this morning, Robert Seiringer, to actually discuss those. Then we looked on at zero momentum with a time-dependent pK function, basically. At finite temperatures, this function determines, but this doesn't cover nicely the effect of recoil, and thereby it's hard to look at the dispersion relation. It's an interesting question, though, because if I say it's a 20 body-bound states, then it should have the mass of 20. Yeah, so maybe one should do some configurational DFT calculation also and maybe study, I don't know, this problem, but we would have some scale separation. So let's take some very light atoms and a very heavy one. Maybe then DFT would actually work in a sense. So it's not solved.